Let's look at a relatively complicated trig integral. The secant and tangent ones tend to be, excuse me, a little bit more complicated. And the particularly complicated case is when the power of secant is odd and the power of tangent is even. Here, the power of tangent is 0. So that's certainly an even number. And so how would we do this one? Well, instead of just a mix of algebra and trig identities, we're going to have to bring in, excuse me, another tool, which is integration by parts. The book, our book, and almost every book has secant cubed, and so you probably want to look at integral secant and integral secant cubed before you look at this, partly because we're actually going to go ahead and just reduce to those answers. And that's going to be our main technique. So this is actually a good example of what's called a reduction formula, where we're going to use integration by parts to take an integral with a certain power and express it as a similar integral with a lower power. And if you do that enough times, you get down to something you already know. So what do we need to do? We need to set up, if we're going to do parts, we need to choose our u and our v. And of course, that's based on, well, let's just put dv here, I guess. And then that's going to tell us our du and our v. Okay. So it's all about splitting it up. So a fifth power, you could split that up into various things. You could let u be the whole secant to the fifth and dv be dx, that's legal. Or you could take some of those secants, put it with u, and some of them with dv. Luckily, here, a fairly standard thing about integration by parts applies, which is you'd really like to be able to integrate the dv part easily without doing a whole lot of independent work. And so it turns out that secant squared is a good thing to choose as your dv. That forces this to be secant cubed. But the good news, of course, is that then v is just tangent x. We chose dv to be the derivative, or the differential, of tangent. So that's good. At least that first obstacle is overcome. Okay, du is now, let's see, that's a chain rule, 3 secant squared x times the derivative of secant, which is secant x tangent x. Well, you know what? Let's simplify that right in place. That's 3 secant cubed times tan. Okay, so now we're set to go. Let me actually copy it down here, so I'm doing it after this sidebar. All right, so uv, remember parts, that's integral uv minus integral v du. Okay, and so uv is going to be secant cubed x tan x minus 3 integral of v du, and so that's going to be secant cubed x tan x dx. Okay, sorry, just totally wrong. V du, it's the bottom. 3 secant cubed tan squared. Okay, I'm not totally wrong. I just looked at the wrong thing. Tan squared x. Okay, we're clearly not done. Okay, so how can we deal with this guy? Okay, so this is where the trig identities come into play. They still definitely come into play, even if you've got parts as a tool. What I'm going to do here is I'm going to express the tan squared. Now, that is an even power of tan, and that definitely, we have an identity that applies to that and relates it to secant. And at first, it might seem a little bit weird what we're going to do, but it's a fairly common strategy. I'm going to use that tan squared is secant squared minus 1. So let me just copy that, but then re-express this as the quantity secant squared x minus 1. Okay, so let me just write that out. I'm going to go ahead and distribute that and even separate it out into 2 integrals. So you got a secant to the 5th x, one of the things, dx, and then plus the minus sign. When I separate this out, it's going to cancel, and you get plus 3 integral of secant cubed x. Okay, now this sometimes, hopefully, if you've done enough examples of parts, you might have already seen this already, but it can seem really weird the first time you see it. I seem to be back where I started. I seem to have made no progress at all. It seems to be circular. I started with integral secant to the 5th, and I'm expressing it in terms of itself. But this is where really basic algebra comes in and saves us. This is our unknown quantity, it's totally okay for the unknown quantity to appear on both sides of an equation. You can just isolate that. So I'm just going to add 3 secant to the 5th x dx to both sides. So I get 4 integral secant to the 5th x dx equals all the rest of it. I'll just copy and paste all that. Okay. Now, have we made progress? Well, it's certainly not, well, oh yeah, then I'll just divide by 4. Let me just do that before I talk about what else is going on. So I'm just going to copy this, but I'm just going to divide by 4 on everything. Okay, so that's over 4, and that's just a 3/4. Okay, so we're not done. The integral signs haven't completely disappeared from the right-hand side, but we really actually have made progress. We were dealing with a high power of secant, secant to the 5th, and we've reduced it to secant cubed. Now, you could do exactly the same process. All just, the 3's turned into 5's and the 4's turned into 2's and everything, to integrate secant cubed. But there, for the case of cubed, there's different ways you can do it, and often you'll see in a book a slightly different way of integrating that. In any case, we're going to go ahead and take advantage of the fact that secant cubed is a known integral. Let me make sure I get the sign right. It is 1/2. So it's kind of, if you look at the formula, we're going to get, it starts out in a way that should look pretty similar. Oh, it's like a fraction times secant tangent. So secant cubed tangent is down to secant tangent. Okay, and then, yeah, it's a plus. Then the really weird one is that the integral secant comes in. And that's just a very special case, but one that I hope you've seen at this point. Okay, and plus c, since it's an indefinite integral. Okay, and then we could distribute the 3/4 if we want. Honestly, that's pretty good. It's a complicated answer. It's just, this is one of the hardest ones. It's one of the funkiest answers you're going to get to something that can be written down in a simple way. And it can show up. It's not super common. It can show up, especially when you look in the next section, at least in our book, which is trigonometric substitution, which takes an integral that doesn't seem to have to do with trig at all, but you get stuck on, and it turns out a good way to do it is to turn it into a trig integral, and sometimes you get trig integrals that are this strange.